hope it stays this way. Okay, so hi everybody. My name is Alon. Is this working? Oh, okay. So my name is Alon. I'm a student of Professor Retzker from the Hebrew University. Today I want to present some work we did with our experimental collaborators at Professor Jelezko's group at Ulm University, titled Protecting Quantum Information via Destructive Interference of Correlated Noise. Now actually, at the last minute, I almost changed the title of the talk because yesterday I was in the Guns N' Roses concert in Tel Aviv. But I think it's probably better to keep it this way. All right, so I think the motivation needs little introduction here. So one of the outstanding challenges in quantum technologies is decoherence. And in the context of quantum computing, that would be long quantum memories and high gate fidelities. But there's another pillar of quantum technologies, which is quantum sensing. Here in this illustration, you can see the Nitrogen-Vacancy center in diamond, which is an atomic scale defect here on a scanning tip, which can be used for magnetic field sensing and spectroscopy. Here, the figure of merit that is kind of the analog of fidelity is sensitivity. It differs in a couple of important ways, but it's kind of an analog. And the fundamental building block of both of these is the qubit. And I want to consider Hamiltonians of the following form. So we have a first term, which is small omega naught, which is the bare energy gap of the transition frequency of the qubit. And it's time dependent because I'm going to let it fluctuate due to interaction with the environment. And this would cause decoherence. And the second term, large omega, is the control, which is naturally time dependent, but I'm also going to consider noise in that. So we need control for doing gates and for doing spectroscopy. But I want to focus on the kind of the quantum memory aspect, so just the prolongation of coherence. And there's a family of methods called dynamical decoupling, which are used for that. So in these methods, we dynamically drive the system in order to decouple it from the environment, thereby prolonging the coherence. And what I'm going to discuss today is a different principle than dynamical decoupling, but I'm going to compare and combine it with dynamical decoupling. So I first want to review kind of the general principle of dynamical decoupling. So really the mechanism here is refocusing, and perhaps the prime and first example is Han's echo. So let me quickly go over that. So in a Han echo experiment, what we have is we initialize the qubit and prepare it in a superposition state on the on the equator. And then we let the state evolve for some time tau over 2 here. And because the energy gap fluctuates and there's noise in that, then the state vector processes at different frequencies, and we lose the information of where the state is, and this causes, this is decoherence. And the next step would be to introduce a pi pulse. This, you can follow the trajectory of the state through the green lines here. This flips the state or rotates the state around the y-axis. And if we then introduce a second free evolution period of the same duration, then given that each state vector processes by the same amount, then all of these arrows would refocus to what is called an echo. And as you can see here, we kind of retained our coherence. Okay, we know where the state is. Great. So now for this story to work, the central feature is that we have the same precession angle in both free evolution periods, right? So we rely on temporal correlations of the noise and our ability to manipulate the system faster than the noise starts to differ temporally. So this is the criteria of refocusing, and we'll go back to that. And just to mention maybe the most common, or one of the most common refocusing dynamical decoupling pulse sequences, which is CPMG. This basically consists of just repeating this middle part of the sequence n times. And one of the important features of CPMG is that it refocuses control noise. So you can think of the green arrows as undershooting or overshooting the desired operation. to below or above the equatorial plane. And given that these overshoots or undershoots are temporally correlated, this sequence refocuses that error as well. Great. So there's another mechanism that we know that can reduce signals, which is destructive interference. Here, the red signal is the destructive interference of the black and gray one. Right? Here for coherent signals, and what I'm going to show you today is that we can do that to noisy signals as well. And if dynamical decoupling or refocusing requires that the noise correlation time is long, destructive interference requires that we have some cross-correlated noise terms and that we can somehow match them and destructively interfere them. So we're going to exemplify this principle by looking at a scheme of driving a qubit with two control fields. And the cross-correlated noise terms are going to be the amplitude fluctuations of these two control fields. Now, generally, driving a qubit with two control fields was introduced in a scheme called a double drive about a decade ago. Sorry. It was also experimentally demonstrated on NV centers and lately on HBN spin defect. And the connection to this work would be not the introduction, but rather the consideration of potential cross-correlations. All right, so let me first review the original scheme and then switch gears to what we did in this work. So what is the double drive scheme? Well, let's say we just have a bare qubit without control. This delta naught of t is the fluctuation of the energy gap. And this will cause decoherence. As we said, the precession frequency fluctuates. Great. By introducing this first drive field, this would be the Rabi amplitude on resonance, we can work in a regime where what dominates decoherence is the first drive amplitude fluctuations. And to see that, we move to the dressed state picture. This is an interaction picture where the Hamiltonian looks like this. And here it's very clear why decoherence is dominated by amplitude fluctuations. This is exactly the same Hamiltonian up to changing x and z. Now, we can repeat the trick once more and drive the dressed state resonantly. In the lab frame, the waveform would look something like this. So it's a drive on the second quadrature due to the sine function here. And the amplitude is modulated by a frequency, which is on resonance with the Rabi frequency of the first drive. And similarly, we can work with a dressed qubit where we see that the second drive amplitude fluctuations dominate. Again, in an analogous fashion, it decouples the previous noise term. All right, so let's now switch gears to this work. So in dynamical decoupling, what happens is that we kind of move from being dominated by the environmental noise to being dominated by the control noise, at least in certain parameter regimes. And this could be beneficial or not, depending on the parameters of the noises involved. But control noise can have structure temporally or between different frequencies that we can exploit. And this is what we considered here. So if these two noise terms are correlated, say because they're going through some similar control hardware, then let's see how we can destructively interfere them and prolong the coherence. So to do that, let's free up this modulation parameter here and optimize it to get the best coherence. Now, this, I remind you, was on resonance in the dressed qubit picture. And the reason is because this is the way to optimally decouple the epsilon 1 noise here. Okay? But if epsilon 1 and epsilon 2 are cross-correlated, then maybe we can detune to reintroduce some of this noise, but in a fashion that destructively interferes with the second term, thereby gaining an advantage. So this is the idea. And indeed, when we follow the math here, if we define the cross-correlation as C here in a standard way, sigma is the standard deviation of the noise, then what we get is that the optimal frequency, or the detuning here, so the detuning, which is this part from resonance, is proportional to the cross-correlation to first order. And the decoherence rate, the first order contribution looks something like this. So let's consider the limiting cases of this expression. So first, if the correlation is perfect, then we see that the first order contribution to the decoherence rate vanishes. This is a feature of clock states. So we in fact created dynamic clock states, and we've actually not just moved from the environmental noise to the control noise. We somehow mixed the control noise on the qubit in order to get improved performance on the dress qubit, which is kind of a hybrid system of the control and the bare qubit. When c equals 0, that is when the two terms are not correlated at all, then we see that we retain the original scheme. That is, the prescribed way to drive is on resonance. And the decoherence rate also makes sense. So this is an important sanity check. But it also means that these principles can be combined, dynamical decoupling and destructive interference. And secondly, this means that if we compare the two schemes, we can isolate the contribution of the cross correlation, and without changing the dynamical decoupling properties of the scheme. And this is the last comment, only if you've asked yourself, wait, but this looks similar to the Bloch-Ziegler shift, otherwise ignore what I'm about to say. So the Bloch-Ziegler shift is a shift that arises from counter-rotating terms that exist. And it has kind of a similar structure if we swap C here for 1/4, for 1/4. But these are unrelated. I mean, they have different physical origin. I mean, one comes from counter-rotating terms, one from cross-correlation. They have different magnitude. One can exist while the other doesn't, or both, or neither. When both exist, they are just additive to first order. So we can just swap this C here for C plus 1/4. All right. So just kind of to pin down the main message, the Bloch sphere of the dress qubit looks something like this. We have two noise terms coming in. They're on X and Y because they come from different quadratures. And the modulation frequency, omega 1 tilde, the detuning of it from resonance, changes the angle on the Bloch sphere where the effective drive axis. Now, the important thing here is that the projections on the effective drive axis are the leading contribution to decoherence. And what we see from this picture is that we can choose an angle such that they cancel out. Okay? So this is the mechanism we are utilizing. And in fact, just to draw it this way and to claim that there is a definite sign relationship between noise terms is a manifestation of their cross correlation, right? Otherwise, it doesn't make sense. And what this means is that we destructively interfere these two noise terms to get an effective noise which is smaller. So to sum up, dynamical decoupling relies on temporal correlations, which looks something like this. And for whoever is familiar with it, so the parallel spectral density at some value tau, let's say, the difference between T and T prime, while destructive interference relies on cross correlations. That is, this term or the cross spectral densities, in this case considered at tau equals 0. Okay. So let's move to the results and implications. So the simulations and the experiments, some of the simulation I'm going to present were done in collaboration with the group at Ulm University, Genko and Qingyun. And I don't really want to go into the NV center experimental setup. For us, it's just going to be a qubit that we can initialize and read out using laser light and manipulate using microwave control lines. All right? So first, a simulation of quantum memory. So to retrace the logic I just described. So in the absence of control, we have a coherence time of about 4 microseconds. Which is just typical NV noise parameters. We introduce the first driving field, and we get a coherence time of about 20 microseconds. Introduce the second one. This is the standard double drive scheme. We get about 220 microseconds of coherence time. And now let's just make this slight detuning for the correlated double drive scheme. And what we get is an improvement by about factor 8 to 1.8 milliseconds. And this is a simulation where the noise is fully correlated, and we got 8 to 10 an improvement factor depending on the parameters. And there's no T1 in the simulation. Let's do it in an experiment. These are Rabi oscillations of the two schemes. So in blue, the standard scheme, and in red, the correlated double drive schemes. And as we see, we move from 250 microseconds to about 2 milliseconds. So again, a factor 8 improvement. As you can see on top here, there's this n equals 0 for the standard scheme and n equals 5 for the correlated scheme. N is just a way to parameterize the shift that we just described that would be necessary. And indeed, if we scan this shift, we see that we had a maximal coherence time at n equals 5. So this corresponds to almost perfect cross-correlation, including the Bloch-Seeger shift, which indeed exists in this setup. And to benchmark this against something, so maybe one of the most used pulse dynamical decoupling sequences is XY8. XY8 depends on a parameter, tau, which is the interpulse interval. So we did a couple of these experiments. We scanned the parameter, the tau, and what we see is that the coherence time maxes out at about 2.2 milliseconds. Okay, so this means that we're pretty close with this scheme to what is very widely used and also have been shown to be optimal under some conditions. But I just want to say that in this scheme, we didn't really optimize the Rabi frequencies, which would be the analog of optimizing tau here. So we think there's actually a way to push this forward. Yeah, OK. Switching gears to a quantum sensing experiment. And this, I'll also make a couple of comments that are important for gates here. So if you're not interested in sensing, maybe it's still worthwhile listening. So again, sensing with the two schemes. Okay, we sense an external AC magnetic field, the standard scheme in blue, and our correlated scheme with the shift in red. And of course, you know, the results speak for themselves, but that analyze the sensitivity, which is the figure of merit. So the T2 here improves by a factor 3.5, and the sensitivity goes like the square root of that. And the second term here is a post-selection term. So the standard scheme was not sufficiently stable to just take all the result. We had to post-select about 20% of the results. That means that the sensitivity incurs a penalty of a factor square root of 5. And the last term here, gamma, is the coupling to external fields. External fields can be the sensed fields or external control fields, which we want in order to manipulate the address qubit. And one of the criticisms against these multi-drive schemes is that they reduce the coupling to external fields. But indeed, what we found is that this attenuation of the coupling is not necessarily the case. And when we've kind of more meticulously analyzed it, we were able to demonstrate a factor 2 improvement with respect to previous demonstration. Great, yeah, thanks. For both schemes. Maybe to put the sensitivity figure of merit in some context that would be familiar to everyone. So the integration time of the time we need to do the experiment for a given sensitivity scales like the square of the sensitivity. So here this means that with this method, compared to the standard method, we can do in one day what we would have done in 2 weeks of measurements, say. And as I quickly said, this gamma would also be coupling to external control fields. So we can do gates in the dressed basis as well. And dressed qubits, as Alex discussed, are one paradigm to doing computing as well. So one last slide before concluding. Here we examined pi pulses of different scheme and compared. So in blue here we have the robustness, the fidelity of the standard pi pulse. Okay, so this shows its robustness. On the horizontal line is the amplitude noise of this pulse. And on red, we have the double drive scheme. So this is not improved on average. And the reason here, the second important criticism against this thing, is that while it prolongs the coherence times, it slows down the operation in exactly the same factor. So you don't really gain in fidelity. But there's a way to compensate the error in standard pulses. One of the common techniques is called composite pulses. And here in orange, you can see Malcolm-Levitt's, maybe the first composite pulse, and which performs much, much better. In green, you can see this works. So it's not as good as Levitt's composite pulse, but it's pretty good. Definitely an improvement. But the crux of this slide is really what happens when we introduce fast noise into the game. Fast meaning that it fluctuates on the time of the composite pulse. And then the composite pulse, of course, fails because it operates on the same mechanism of refocusing. So it needs temporal correlations. While our new scheme here still performs and, in fact, outperforms. So to summarize, destructive interference-based noise mitigation relies on cross-correlation and improves a bunch of different figures of merit. In fast, when it exists, it's always good to utilize it, and specifically for fast noise, it might be extra beneficial. It's fairly general, so we believe that all of qubit-based platforms can use it, and specifically superconducting qubits are quite popular, so hopefully in that as well. And in the future, there are a bunch of things we're thinking of, but I want to say maybe like 2 things that were measured recently. So the Oliver group measured cross-correlations in noise and cross-spectral densities in superconducting qubits, and the Degen group at ETH also measure these quantities in NV qubit registers. And we hope that this would at least kind of motivate a way. Let me rephrase that. Of course, this is information that could be utilized in the design of the system and the control protocols, and we hope to look at that, and that looking at that would be fruitful using this mechanism and context. So I want to thank my advisor and the group at Hebrew U and Professor Jelezko and Genko and Qingyun, as well as various fundings. And I want to thank you for listening. And if there are any questions, I'm happy to take them.
Thank you, Alon.